So let's go into some details about how we would seek predictability of rainfall, let's say at subseasonal timescales. Rainfall, as I said, is an interesting variable to go after because it's always small scale, but then what does that mean? Where is it smaller scale? Where is it a larger scale than some idea of small scale rainfall, right? Compared to temperature, the decorrelation scales of rainfall are much smaller, right? So this is from the book, A Simple Yet Instructive Decomposition of R bar, which you can think of as seasonal rainfall average, let's say over a particular grid point, or of all of the country, or could be a spatially homogeneous region. So R bar involves the product of the number of wet days, NR. So let's say that's rainfall greater than 1 millimeter, and the mean rainfall intensity. So if you take the total rainfall and divide it by the number of wet days, then you know on average how intense the rainfall was during those days. Very simple, right? I bar reflects both the instantaneous rain rate, which is high for convective rainfall, and the duration of rainy events. So how long they lasted. There are differences between land and ocean, for example, which is related to spatial scale and the movement of the rain-bearing systems. So you can either have rain that is convecting locally and pouring for hours, or you have a storm that's passing by, right? So on average, the duration of rainfall, I think, is about 4 point some hours on land and 6.5 hours or so on the ocean. So the other thing to notice here that by nature the rainfall intensity is not as spatially coherent as the mean rainfall or the number of wet days. Okay, so regions that get good mean rainfall obviously have a large number of rainy days. So the decorrelation scale or the correlation scale or coherence, and various ways you can think of this, are much higher for R bar and NR than for I bar, which is the mean rainfall intensity. So this includes mesoscale convective systems and so on. So to understand how we can use time variability at a particular location versus spatial coherence to seek predictions, predictable signals, which you can also think of as a signal to noise ratio being higher, we look at this example here. It is basically daily mean rainfall in millimeter for 2.25 degree grid points from the IMD dataset for Mumbai and for New Delhi. Mumbai is a coastal city with a lot of rain. New Delhi is right in the middle of the subcontinent and doesn't get as much rain. And there are some details about eliminating dry days where there is no rain above 5 millimeters for 10 days and so on and so forth. Quickly zooming in, if you look at the different years, so here it is, I think, Mumbai and Delhi for 1983, 1988, which were both wet years, which means above normal years, and 1986 and 2002, which were both dry years. What do you want to look for? The red lines here are the long-term mean onset of rain at each place. So Mumbai and withdrawal Mumbai, onset in Delhi and withdrawal in Delhi. So does that give us any sense of predictability? So you can see that in Mumbai the wet and dry years have similar onset days, hardly any difference, whereas the wet years seem to have a later withdrawal here in blue, for example, compared to the climatological mean. The withdrawal was much later in 1983 and 1988. Whereas if you look at the dry years of 1986 and 2002, 86 was an El Nino, 83, 84 was an El Nino, but it was not as dry a year because of other things happening. Potentially the Indian Ocean dipole, for example. And you can see here the withdrawal happens much earlier, even though the onset happened around the same time. Whereas the relation is not so simple for Delhi. So in Delhi, the normal or wet year of 1983 had a slightly earlier onset than long-term mean and a slightly later withdrawal, but here it had a much earlier onset and withdrawal happened at the same time. So the length of the season and the number of rainy days are not that systematically related over Delhi, so you cannot look at number of rainy days and intensity of mean rainfall or mean rainfall intensity and so on. And similarly here, the onset couldn't even be properly defined in this year, and here the onset was much later or defined in a very erratic way, and withdrawal happened later. So basically that means Delhi, it's hard to rely on defining a season with an onset and a withdrawal to define wet or dry years, but this can work for Mumbai. Okay, so you can see the differences between the two places. So then what you go for is the spatial coherence, and then you see if there are ways to look for large-scale conditions or climate modes which modulate spatial coherence, so that then you can still look for weather within climate, which is the way we are doing it in terms of seeking subseasonal forecasts. So here mean seasonal variation is shown in blue, and spatial autocorrelations of interannual ranks of mean amount, so it's called bold red here, but actually it means green. So the bold green is showing autocorrelation of interannual ranks of mean amount. I will say what that is in a minute. And frequency of wet days receiving 1 millimeter or more in a 500 kilometer rain in running 15-day windows, averaged over summer monsoonal regime from a clustering of the mean annual cycle across India and underlined by black contours in panel B and E here. Okay, so those are the regions we are looking at. What else we want to see here? The thin red line. So here the thin green line is the frequency of wet days. So here is the rainfall, and it peaks in July, August, as we know. The onset happens somewhere at the end of May and July. So the red lines are shown here. Make sure we understand this figure is kind of long caption. The vertical red line in A shows the center of the 4 15-day windows used to extract leading EOFs of amount of ranks in panel B and E. So essentially, it is ranked instead of taking amounts of rainfall. Rainfall is ranked. So you take a center point and you say what is the mean amount, and then you rank the other points based on the relative amount of rain with respect to the chosen point. And then you have a 15-day running mean running window over a 500 kilometer radius. The analysis is also done with different scales, 100 kilometer, 1000 kilometer. It doesn't change the results. The main point you want to see here is that if you look at these months going from April through to November, the coherence is high during the onset period here and during the withdrawal, and it drops to its minimum during the peak rainy season. Okay, so it's as if there are large-scale dynamics that are setting the onset, and then there is high coherence over space, 15 days or 500 kilometers. But when it's heavy, intense rain at the peak of the season, there is no spatial coherence. So it's as if you are setting the envelope to have rainfall season on, and you reach the peak season, and then you have lots of mesoscale convective systems, moving storms, gravity wave impacts, soil moisture impacts, and so on and so forth. And similarly, the intensity of rainfalls, you can see here, it's the I'm losing track here, but the frequency of wet days receiving 1 millimeter increases here, flattens during this period, So lots of them are happening, not decreasing, and then they increase again towards the withdrawal. So if you look at the EOFs of those periods here, in the beginning, in the middle of the peak of the season, at the beginning of the peak and the end of the peak and withdrawal, you can see that the onset here has large spatial coherence with this north-south, east-west pattern, and withdrawal similarly has large-scale pattern, whereas the spatial coherence seems to reduce in size or basically becomes much less coherent at these scales of 500 kilometers in 15 days during these peaks of the season. Okay, so again, the dynamics of it has to be understood, but in general, even the wet and dry years of the monsoon tend to have better coherence than a normal year. So there are some dynamic constraints there in terms of large-scale structures governing the dynamics at the beginning and at the end versus in the middle where the season is on and lots of convective systems are forming with no spatial coherence. That also explains the distribution of the rainfall that we saw with lots of normal and dry and wet regions very close to each other. This kind of inhomogeneity is argued to be increasing over time. So we will leave it there for now. But just think of the idea of using spatial coherence and the modulation of this spatial coherence by climate to look for predictability at subseasonal timescales. So 15 days is kind of getting into that range.